Hi, I'm Josh Goodhue, and I'm an electrical engineering major at RIT.
Hi, I'm Bautai. I'm a computer engineering at RIT.
And we are going to be showing you a state machine that we've made in the game Minecraft. Now, Minecraft is usually a game played by little kids, and they build things in it, but it also has a built-in logic system using Redstone. So, the way Redstone works is I'll explain it. So, it has two states, either unpowered or powered, also known as 0 or 1. This lever powers or unpowers the redstone. Same with this torch. The redstone wires can travel over blocks. Now, a NOT gate can be created when a torch receives power. So the torch is on, it receives power, the torch is now off. So you can see this here, the output is 1 when the input is 0, and when the input becomes 1, the output becomes 0. Now, redstone also has some limitations. It can travel about 15 blocks before it dies out. You can see at the end here that this redstone is not active. So this is why we have these things called repeaters, which essentially serves as a powered diode, refreshing the signal and continuing it on for another 15 blocks. So we can use our NOT gate format over here to create a few different gates like this AND gate, which is built with 3 torches and some blocks. So to prove that it works, so right now the input is 0, 0, neither lever is powering the redstone. When the input is 1, 0, the output is still 0. When the input is 0, 1, the output is still 0. But when the input is 1, 1, the output is now 1. So this functions as an AND gate. An OR gate can also be created. You don't need these diodes, but we use them so that the output of this does not affect the output of this. So right now, both inputs are 0, and the output is 0. With an input of 1, 0, the output is 1. With an input of 0, 1, the output is 1. And with an input of 1, 1, the output is still 1. So two very important things that we'll be using in our state machine over there are a D flip-flop, which is this, and a clock. So first off, I'll explain the D flip-flop. So this lever functions as the clock, and this lever functions as the D input, and this redstone functions as the Q output. So this is a rising edge flip-flop, meaning that so the clock is inactive right now, the clock is low, so the input, as you can see, is changing, but the output is staying as 0. So if the input is now 1 and then the clock goes high on that rising edge, the output becomes 1. If the clock goes low again, the output will stay 1, and the D input will not be able to affect it. So you can see how that works. Okay, now the clock, let me just reset this clock so I can explain how it works. Just wait for it to run out here. So the way this clock works is I put an input in, turn it off, and the delays of these repeaters create a clock function. So, alright, so I'll give the floor to Bao to explain how our circuit is set up here.
So here you can see that we use the logic gates and the entities that we've just explained to create a state machine. This state machine will produce an output of 1 signaled by a beacon of light when the input after 3 clock cycle is 1, 0, and 1. So for a state machine there are 3 parts. The first part is the input logic, as you can see is over there with all the gates. The next part is the D flip-flops. Here we have 2 D flip-flops enclosed in 2 cases, and the last part is the output logic, as you can see over there. So for this, the input logic is determined by the equation that we've laid out, which is the equation for Q1 is Q1 naught, Q0, and X naught, or Q1 and Q0 naught and X. the input equation or excitation equation for Q0 is Q0 naught and X. So as you can see, the input equation for each flip-flop involves the output of a flip-flop or another. So here we have the output of Q1 going into the input logic, and here we have the output of Q0 going back to the input logics. And now Josh will explain to you how the clocks work.
Okay, so over here we have our clock setup, which is basically a bigger version with a little bit more delay of the clock we had over there. It's a relatively extremely slow clock because we'll be doing the inputs manually of the toggle. So the clock would work the same way. I activate the lever, which would then set this, and the clock ties into both Q1 and Q0 here. Going in the bottom, you can see the internals of this is pretty much the same as the D flip-flop I showed you over there, except this clock has an indicator, so the clock signal travels up here, so when the clock is high, it also lights up these lights to show that the clock is high. So we have an idea when that rising edge is. The same thing happens over here. So when the clock is high, it lights up these lights, and when the clock is low, those lights turn off. So the way we're going to be telling whether or not our Y output is successful is with this system. So as Bao previously explained, the output equation is Y equals Q naught ANDed with Q1, which is shown by this AND gate here. So when both Q naught and Q1 are high, the piston activates, which then in turn activates the beacon, which creates that large pillar of light, which is how we will know if our system was successful. As you can see, when it's low, the system deactivates and the pillar of light is no longer there. So we're going to be going over here and doing the equation, which Bao previously said was 101 to get this thing up and running. So I'm going to wait to see what my clock is doing here. So there's a rising edge, there's a falling edge, so I'm going to want a 1, so the rising edge kicks in, so the 1 is input to the system. Falling edge, so my next input is going to be a 0, so I just leave it because by default that's 0, so my 0 has then been input, as you can see over here by the output of Q1, and the next is a 1, so I flick that on, the edge rises, and you can see the piston goes up. So now I turn this off, and on the next clock cycle, by default a 0 is input, and it should turn off, which it does. Alright, so that is the state machine we have created in Minecraft. I think we've about summed everything up. So, from Josh Goodhue and Bao Thai, we say good night.